Okay, so in the last part, we talked about some fundamental parts of JAX, and we did it in a sort of abstract way. We use these sort of synthetic little problems. Let's now go through a more end-to-end problem, an optimization problem, and it's a pretty simple one. It's just solving y equals mx plus b, and arguably JAX is a little bit overkill for solving y equals mx plus b, but especially on a large compute infrastructure. But I think it's really interesting to think about a very, very simple problem and sort of go through these sort of steps, because it helps us understand something about the libraries and ways of representing models without having to worry about too much about the model. And we certainly won't have to be waiting around for long convergence or something else. So we're going to be going through Colab again. And this time, I'm actually, just for the hell of it, we're going to change to a TPU. So we're actually going to be using a TPU in this case. And I've actually already connected here. Using the TPU is pretty straightforward. We just have this idea of, a little bit of setup we need to do where we need some imports here. But what we're going to be getting now is 8 devices like we had last time. But these times they're actually 8 TPU devices. So each TPU sort of rent has these 4 chips on it. Each chip's got a couple of cores. So the sort of minimum thing you get with a TPU is these 8 devices. So it's good to be able to understand how to do things like the pmap we're going to talk about, because it's a good way of making use of this compute. Okay, so let's, like we'll start with something really simple. We're going to start with this basically a simple line. So what have I got here? I've got this very simple function for defining the line, y equals mx plus b. I'm going to define x, which is part of our input data. It's just 128 values, not very big, in some range. I've got true value of my line. Basically, this is what we're going to be hunting for, these 2 parameters, m and b. I can calculate some true values, and just for the for interest, we'll add a bit of noise. And here's the line we're trying to fit. And everything we're going to be doing in this series from now on is like trying to find those 2 values, m and b. And here's a really simple model. We're going to start with 2 parameters, m and b. This is what we're exactly after. Cool. So we can calculate a predicted value for y by running y with the known x and with our model parameters instead. So what are we going to do to solve this? Well, let's go through a really simple gradient descent to do this. And to do the gradient descent, we need a gradient to work on, and that's something that JAX can give us. So let's work out how to do that. We'll start by using grad in a really simple way. So this is a common sort of pattern we'll see. We have a loss function. So this is how do we sort of calculate a loss for a true value and a predicted value? But when we're talking about gradients with respect to parameters, we need to sort of formulate this a little bit, and we're going to write this loss function as loss with respect to parameters. So what does this get? It gets the x, x and y, which is the true data, and our model parameters m and b. And what we do is we just calculate the y predicted value from those parameters and just return the squared loss. So the gradient we're going to calculate using grad, and we're going to run it on that function, loss with respect to parameters. And one little difference we're going to do here is that previously when we were calling grad was always expecting to calculate the gradient with respect to the first parameter. But in this case, what we need to do is, well, we don't actually want it with respect to x, we want it with respect to our 2 parameters, m and b. So we can tell grad that by saying the args, we don't want the 0th one or the third one. We want arg 1 and 2, which is m and b here. And so what grad will do is it'll provide us that. And because we've asked for 2 arg nums here, when we call this function, we get 2 values back. This is these 2 values. And if we call it with respect to the true values, we get a small gradient. And if we call it with respect to the model, we get a large gradient. Okay, cool. And I guess these gradients here correspond to the irreducible thing from the noise. Okay, so we can use this for a really simple training loop, very simple training loop. And this is a classic training loop we use in lots of places. This idea of we calculate gradients for whatever our model parameters are now, and then we have just basically an update step. And you can see this update step here. It's the same update rule for all the parameters. We've got a current parameter, we've got some sort of learning rate, we've got a gradient, we're going to bump the parameter by that gradient multiplied by the learning rate. And we can see we do that for all the parameters. This is pretty standard. And just repeat. And so for true values, minus 1.5 and 2, we sort of converge, we're converging towards that. We're getting there. So it's a pretty simple problem, unsurprisingly. Now, one thing to straight away see here is that our model has m and b, which doesn't have many parameters. We've only got 2 parameters, but that's not going to take us very far because, and even the simplest model will have many, many parameters. So what we're going to actually start to do is not deal with parameters directly in their form like this, but instead to put them into dictionaries. And Jax provides some tooling for doing that. It falls under this name pytrees, where a lot of the operators can work instead of directly on parameters, on dictionaries of parameters. And in fact, the dictionaries can be nested dictionaries. So you might have, because you've got concepts like layers, for example. So you might have a dictionary that has many layers, and then the layers each have their own parameters. And we're going to operate sort of on the leaves of these trees, these dictionaries in dictionaries. So we're going to reformulate things a little bit. We're going to say the y actually takes parameters directly, and then we sort of pull them out, the parameters m and b, when we do the calculation. And then our loss function is with respect to those parameters. So we're not going to pass m and b directly. We're just going to deal with params. And the good thing about this is that things like grad understand this structure. And so when we do a gradient call here, and we've actually gone back to not putting argnums in because we want gradients with respect to the first argument, which in this case is the parameters. So when we ask for gradients of something using the true parameters, we get the same structure back. So we were passing this dictionary with keys m and b, and now we're getting back a dictionary with keys m and b. So this we'll see this a lot, this idea that when we have these pytrees as the unit that are being passed around, they sort of conserve the structure. So what we could update our little learning loop here to do this, but let's jump straight into some data parallelism approaches. So what we're going to do is this x and y currently are 128 elements long. We're going to reshape them a little bit to make use of pmap. The first thing we need to do is pmap, remember, operates in a way, just refreshing from last time, pmap changes the computation to say we're actually going to run on multiple devices on different combinations of your input, depending on what you sort of want to do. Maybe you want to parameterize in such a way that you broadcast some of the parameters. Maybe you want to parallelize on the leading or other dimensions of some other parameters. So what we're going to do is we're going to reshape our x and y here into, instead of being one thing that's 128 long, it's going to be 8 by 16. And that 8, the leading axis here, corresponds to the 8 devices. So what we're actually setting ourselves up for here is this idea that we're going to be doing data parallelism, where each of the 8 devices is going to be working on 1/8 of the data at the time, and 1/8 of that data is 16 values. So we're going to be running this parallel gradient calculation where each device only looks at 16 values, and then we're going to deal with the sort of assembly of those gradients later. So it's pretty simple. Oops. Do the reshape. So what do we get when we have reshaped this x and pass it through this pmap? So what we were getting before, in the non-pmap version, before we pmapped, we were getting just one gradient. But what we're getting now is we're getting a set of 8. And that 8 corresponds to the 8 devices. So what's happened here is I've said, just refreshing what we've done here, we've said pmap, where I want to parallelize on the second or the 1 and 2 arg, which is x and y. So each device is getting 1/8 of the data, that's 16 values. And then we're basically assembling them back in this sharded device array. So these values here, these 8 values, correspond to the 8 gradients that were calculated, each of which corresponding to 16 instances in the data. So this first one here corresponds to basically the first row of x and y, and this one corresponds to the second row of x and y. So at this point, we've basically calculated the gradients with respect to 1/16 of the data each. And the classic way of assembling this in a data parallelism idea is just to sum the gradients. It actually works. So what we're going to do is we could, this is the naive way to do it to start with, we could calculate those gradients in parallel, and then we could do our own little dictionary comprehension here to basically say for each of the leaves, each of the values in this dictionary, let's apply a sum. And then rebuild that dictionary. So if we've got a dictionary with keys m and b here with the vector, we just basically sum them up and go back to 1. Now again, this idea of dealing with parameters in nested structures and then wanting to apply a function across all the leaves in that structure is something that we sort of will be doing lots and lots and lots. So there's a whole in multiple forms. So there's a library of sort of support for doing this. It's called TreeUtils that comes as part of Jax. That sort of gives us the ability to do this in a slightly cleaner way. So what we're going to do, if I run this, it ends up getting the same effect. What we're doing basically is saying, given this tree structure G, actually run the sum on all the leaves. And it's actually slightly different to what we did before, because here I said explicitly I want it for the values for the keys. This one's a little bit smarter. It actually can maintain a nested structure. So again, if that parameters had multiple layers, each of the layers having multiple sort of M and Bs and who knows what else, then the tree map would actually sort of retain that structure. In this case, the structure is very flat. Cool. So now this is where things get really interesting with pmap. So far, everything we've been doing is a completely independent calculation. So we did this independent calculation, 8 devices, 1/16 data each. And then we're sort of, at the moment, doing this, what feels a little bit clumsy, we're pulling it all back to do the sum. Well, it turns out the sum is something we can actually do in parallel as well. Because even though we're doing everything in sort of independently at the moment, we've done with pmap, it actually turns out that there's ways of representing compute in these independent pmaps calls that involves cross device communication. So there's a whole bunch of actually primitives for doing it. And the one thing we want to do here to start with is actually to sum these gradients. So, because again, the motivation is to move as much as possible into the pmap, because the more we can do in parallel, the more we can sort of make full utilization of all the devices at once. So let's change this just a little bit. We'll change this a little bit. We're going to include one more line. We're going to actually include this this tree map line like we had before, but now it's inside the pmap. And rather than using J and P sum, like summation, we're going to use this other operator called P sum. This is a parallel sum. So let's again go from the top. What we're doing here, we had our mean squared loss function, and that is now being put inside basically this pmap, and it's been put in inside the pmap, so in such a way that the first argument to this call, this pgrads, doesn't get parallelized in any way. That's the parameters. So we're shipping the parameters to each of the 8 devices. But as part of pmap configuration here, we're saying for the second and the third arg, the x and the y, we want you to parallelize on the 0th axis. So what basically is happening here is that remember x and y are 8/16. What this is doing is basically changing this behavior of this function so that each of the parallel calls only gets 1/8 of the data. So this will be run 8 times. The parameters will be copied totally, and the x and y will only get 16 values. And basically, but they'll be running in parallel. Yeah? So we're going to calculate the gradients, and like we saw before when we did this, we got these different values for each gradient, and that's because they're operating on 1/8 of the data. Now what we're going to do, still within the pmap call, remember, still within the pmap call, is this gradient sum using this psum, and psum operates across all the devices. So what happens here is an OR reduce happens between these devices, and we actually get all of them sort of becoming lockstep, because now they all contain the sum. And when we return those gradients, we get the 8 values that are coming back from all of them. But because of the psum now, they've all got the same value. So what's happened here is we've sort of we've copied the parameters out, or calculated gradients, sort of then done a summation across the whole thing, so everyone's got the same value, and then sort of return those gradients. So we're slowly getting towards this, full parallel update. But this sort of stuff is pretty amazing, given how much code we've had to write here. The fact that we're now able to take this very simple function, like this loss function, and just using these couple of things, like a pmap or a psum, we're talking about now this distributed compute that is being orchestrated in a very complicated way. And we're not having to do very much here. There's not a lot of code we end up writing. And so as these TPU cluster sizes, you can imagine, get bigger and bigger, this is a huge amplifier for us, because, the large TPU slices, we can get a very, very large. So making use of this large amount of compute with such trivial stuff is pretty amazing. Okay, so we can start to also do the update as well. So so far we've done the forward pass, the loss calculation and the gradients. We can actually start to do the update. So if we look here, we're going to do one more little bit here inside. Again, remember, we're always trying to do it as much inside the pmap as possible. We can actually do the update rule in pmap as well. So what are we doing here? This is a little bit different. We're introducing another thing, all new things all the time. This is another TreeUtil we're going to use called tree multimap. Because remember before, way back when we were doing the learning update, when we had the model, let's actually go all the way back here when we were doing this one. We were applying this function, this learning rate, this learning update to all the parameters. So what we can do now is we can say, well, we've got this nested structure now that represents the model and the gradient, and we can do a form of a map where we sort of assemble these together in one go. So let's come down to here. So here we are back again. we're going to use this tree multi-map, and tree multi-map, a bit like the map, applies a function, but this time it applies it to 2 inputs that sort of, goes together with. So the update we wanted to do here, we're going to say, given a parameter and a gradient and a really simple learning rate, return the new value of that parameter. And we want to map this function, this update function, over both dictionaries, the parameters and the gradients, and each of them will be applied here. Now, and this works because the key set, basically you can imagine the nested key set, the structure, the hierarchy for both parameters and gradients are the same. So this will be run for the B, this will be run for the M, and if we had a very complicated structure, it would work. Now what we do at the end of this is we're returning these updated parameters. So, and like we had before with the last bit with the pmap and gradients, you can see how we're getting back the same value. The value, because what's happened is the parameters got shipped out to all the devices. Gradients were calculated in parallel. The OR reduce happened, so they all have the same gradient. And then this is now being happening in parallel. But because the parameters were the same, because we shipped out the same parameters at the start, the parameters all get updated by the same gradient, and we get back this same value here. So each of them sort of return, because pmap will always return the 8 values. Okay, cool. So there's only a little bit more we need to do here, but before I go further, I just wanted to add one little bit of extra flavor around how this scales up even further. So far we started sort of with the single device stuff we talked about. We're now talking about these 8 devices on a single TPU, and this behavior of psum. The next sort of hierarchy up is this what we call a pod, and the pod is many TPUs, sort of these TPU devices and hosts assembled together. And what we're going to do is a quick demo where we use not just one 8-device TPU, but 4 8-device TPUs. This is a pod slice called a V832. So I'm just going to really really quickly, stop sharing. And I'm going to switch over to another machine, which is a little bit weird, just because I have the configuration here. So I'm going to share this slightly different machine. Okay. So what we're looking at here is terminal windows, so SSH windows on 4 hosts. And these hosts are connected. And we're just using tmux here to synchronize commands. And so what I'm going to do is I'm going to run Python on all 4 of these machines. And so I'm just going to be literally typing in. And so I'm going to be doing things. Python is like a really simple shell, I guess. And we're going to be simulating what would be happening if we're running a program basically on each of these 4 hosts. But these are different hosts. And we're going to run the thing we were running before, basically. So it's got a bit of setup, and it's going to be literally cutting and pasting. So we're going to be importing jacks like before. This time I'm going to do a little bit more. There's this other pod setup we need to do. I'm not going to talk too much about that. But just like we had before, we've got all this jack stuff. But now what's interesting is we've got these 4 hosts that are, so this is, again, they're 4 SSH windows to 4 different machines, multiplexed under tmux. They're all in a way connected. So when we talk about using things in jacks, like here I've asked for the jacks host ID, they're all in this mesh together. So you can see this host ID actually is returning 4 different values here. So before, when I ran things like devices, I could see the devices are on my machine. And if I run devices here, I see each of these machines has 8 devices. So this corresponds to, if I just actually just run a link here really quickly, they sort of have 8 TPUs attached to them. But what's interesting is they also have visibility over the entire set of 4. So even though I only have 8 devices, local devices here, I actually have access to 32 devices because each of the 4 is actually connected. So this gives us another hierarchy of compute we can deal with. So let's go through what we were doing before. Oops. Let's just build our line like we did before. That's just a bit of a fail, cut and paste fail. So the same thing we were doing before. We got a line we're defining. We got a bit of data. This time we're going to use the JAX host ID you can see here to seed the random number generator, which is why we're getting slightly different values for the Y true. So again, these are 4 independent machines. They've each got 128 values, but for X and Y. But because we're using the host ID as the seed, they've got subtly different ones. Okay, so we do the same thing we did before, where we do the reshaping of X and Y. So now each of them is sort of 8 by 16 values instead. And we're going to do the first, well, the next piece is the loss function like we did before. So if I calculate, this is the same thing we had basically before. We'll get this very simple loss function. If I have some model parameters that are shared across the machine, so each of the machines is using the same model parameters, if I calculate the loss, I get a different loss. And that's because, again, the Y values were seeded by a bit of random noise that was seeded by the host. So they're similar, but they're not exactly the same. So let's do that first piece like we did before, where we calculated gradients. Oops, in parallel. Let's see if I can work out how cut and paste works. Okay, so this is the same thing we did before. We're doing a parallel call to get the gradients basically. So I'm pmapping over my gradients function that I've made here, parallelizing over my X and Y. And for the start, I'm just calculating the gradients. I'm just literally returning the gradients here. And you can see that as we had before, each of these hosts having 8 devices is calculating a gradient with respect to 8 lots of 16. And again, they're all different across. So we've got 8 on one machine, we've got 8 on this machine, we've got 8 on this machine, and each of the 4 hosts, because of that seeded difference, has a different set of 8. So what's interesting is about these hosts are all, at the moment, these hosts are all acting independently. So, if there's things like, complicated, well, often CPU bound input processing, for example, so loading the data up, each of these hosts would be doing things completely so far independently. So they're all operating on different sets of data. They've all loaded it or done whatever they needed to do. They've calculated gradients. We'll get to this point. Now, if we do the p-sum, like we did before, where we've got the additional piece, which is basically just that p-sum over the gradients. At this point, that all reduce is not just happening across the 8 devices. It's not just happening across the 8 devices within one of these hosts. It's operating across the entire mesh. So this all reduce now happens across all 32. So until now, we were all running in parallel, and now we get this all reduce, which means that all 32, not just the 8 locally on the machine, all 32 have contributed. So that's very, very powerful, because it means that the absolute minimum amount of work has basically had to be done to make this data parallel approach happen. So, we've got this hierarchy now of sort of compute. We've got this local sort of driving program. We've got these multiple devices, and then we've got this sort of pod structure where we've got multiple hosts, each with multiple devices. It's pretty amazingly powerful. So that's the end of this sort of demo of the pod. Let's go back to the CoLab basically now. I'm just going to switch around a little bit. Okay, so right. So let's continue here. So we're back to this idea that we had the gradients being calculated and the parameters being updated and all being sent back. We are almost close to everything being done in sort of one update loop. The last thing we sort of really need to, one thing I want to call out. So that idea of having the SSHing on the machines and sort of having the parallel program running and having the TPU just basically ready to go. This is still something that's a little bit in sort of not publicly available yet, but I'm going to have a link in the video and on the blog here about this Jackson Cloud TPU, where you can do an early sign up and get access if you want to play around. There's a really good talk as well by James and Sky on this, and I'll link to that too. Cool. So the last thing we need to do basically is to make sure that the parameter update operates in the way we want. We've got this classic idea. We see this a lot. Parameters equals an update of the parameters, and we basically run that while true loop. The reason that wouldn't work at the moment is because this version of the parameters coming back from the 8 devices is this sharded device array. And, they're all the same value. Each of the devices was seeing the same model. You can see each of them has the same value of their B, but they're all sort of coming back. And so what we're going to do is basically one little step at the start, where instead of sending out the model parameters as this dictionary, we'll send it out in this sharded replicated form. So this is just like a little setup. We can make some really simple utilities to help with this. So let's say our model parameters, we want them to start to be like this. You know, M and B are like this. We can run this little function, a very simple replicate function that I've defined here. What the replicate does is basically take your value, like 1, for example, and just replicate it, like tile it over some number of replicas, stack it in. And then we call a pmap, this is a bit wacky, we call a pmap with a no-op, because a pmap with a no-op, if you've got that leading dimension of the right size, basically turns it into a sharded device array. So by running these two together, this idea of this stack of a copy and then a pmap, we turn these model parameters into what were just scalars into a sharded device array with that value being replicated. And remember what the sharded device array is. It's an idea where it's a representation of the values that are on the devices. And so what we do here with a sharded device array, when we've got 8 values that are all the same, we're basically saying that all the devices now have a copy of this 0. Now, you know, the model parameters aren't terribly big here, but, you know, as this, again, the models scale up, these sort of things get more and more important to say that there's a minimal minimal communication between machines and your host. And in this case, they all sort of have a copy of the model, so to speak. Okay, so and while we're sharding things, we might as well do that same thing with the X and Y. And what we've done with this idea of, again, that no-op pmap, before, actually a little bit above, we had a value that was the right shape, 8 and 16, but it was still being sent all the time. Now what we're talking about is if things are the sharded device array, now that data is sort of living in the right place. It's living on the devices. So this is the last sort of step now, that we've got everything we need to run in this very, very distributed way. Let's go through them again. The model parameters, we replicated them across all 8 devices using that little trick there with the stack and the pmap no-op. So that means that all 8 devices have a copy of the parameters, the same parameters. Cool. So the data, so the X and Y, are sharded across the devices. So we took that 128, we resized to 8 by 16, and we've done this pmap basically to spread it out. So each device has on it a copy of 1/8 of the data. Cool. And we've now got a way to do all the parts of the update. So the forward pass, the loss, the gradient calculator, the parameter update can be done with minimal sort of communication between machines. So this is what it looks like. It's not terribly a lot of code, but let's again go through it. It's pretty amazing. Again, we've got that P update. This time now, before we had a none for the parameters, but now we're actually going to say, well, because it's sharded and they're up on the device, we actually do want to parameterize across that first value of parameters. So again, what do we do when we're talking about the in-axis here being 0? We're saying parallelize over the first, that batch dimension. So what's going to happen is that this P update is going to get 1 copy of the parameters. It's going to get 1/8 of the X, and it's going to get 1/8 of the Y true. So we do like we did before. We calculate the loss. We do that cool P sum to basically say, let's assemble all the gradients. So now every machine, even though they calculate independent gradients for their independent X and Y, they now have all the same gradients. And after that, we will apply this update. Now they all have the same parameters, and they're going to apply the same update with the gradient. So now they still all have the same parameters, and we're going to basically use that little multi-map to do that, and then we're going to finally return it. So this is the sort of loop we want to see. We've got this model parameters, and then we return the model parameters, and in this case we're using that value and gradient so that we can get the loss, and we're just going to return that loss too. Okay, cool. So when we do this, we run our model, and unsurprisingly, we're starting to get towards convergence. You know, maybe the optimizer here wasn't great, so we're getting there. But you know, what a way to solve y equals mx+b. We've got these super awesome TPUs. We've got 8 of them. We've done the right thing in terms of divvying up our data and our parameters. We've shipped it out to the devices, and then we're just calling this really nice simple call here, which is just orchestrating with pmap via this amazing XLA technology to just do this data parallel approach. Awesome stuff. So that's sort of our wrap up for this part. In the next part, we're going to talk a little bit more about, we're going to be straying a little bit away from JAX and talking more about the fact that in this model, we sort of defined things and it was a little bit clumsy. We had to do our own y equals mx+b. We need a bit more of a neural network framework to sort of to deal with. And we're going to use one called Haiku. And we also did this optimizer here, our little optimizer, double quotes, was pretty clumsy. So we want to start to make use of another framework for doing optimization too. And we're going to introduce Optax, which comes from DeepMind, to do this. So let's extend this a little bit using a little bit more standard neural network sort of definition and a more sensible optimizer.